To summarize, Chapter 15 has focused on oscillations, and in particular, most of that has been simple harmonic motion, or SHM. And that is when you have a sinusoidal oscillation with a fixed period t and amplitude a. So we have talked about other versions where amplitude is changing, but simple harmonic motion, you must have a fixed amplitude. We can relate frequency f to period, and we also can talk about angular frequency omega. Note that we also used omega before to talk about angular speed back in chapters 4 and 5, or just 4. And now we're calling this angular frequency, relating to normal frequency and period. Whenever we have simple harmonic motion, we're going to have a sinusoidal response, and we express it as cosine of omega t plus this phase constant. And again, phase constant comes from initial conditions. It's not physically an angle, it's a mathematical parameter. And a, the amplitude, also comes from initial conditions. It's not simply the initial starting position, since you might also have an initial starting speed, which then influences both a and phi naught. To find the velocity, we would take the derivative of this, and then the constant we have out in front is the maximum velocity that it ever reaches. And note that this is sine, so when you plug in, for instance, the correct value of t, depending on what your phi naught is, that this becomes 1. And there's obviously a phase difference between sine and cosine, so that when you're at your minimum position here, a position of 0, that's when you would have your maximum speed. Note that maximum speed is also going to then be multiplied by is equal to the amplitude multiplied by the angular frequency, and that's coming from taking the derivative of this. We can then look at the acceleration, which is of course the second derivative of our original function, which you come back to the same form. Derivative of sine is cosine with another minus sign. And so we see that the acceleration is in fact negative omega squared of our position. And this is really important since this then relates to the equation of motion, and we've said that any type of simple harmonic motion starts from an equation like this, which we typically wrote as a differential equation. Dynamics in general are the study of forces, and what we've seen is that all simple harmonic motion has a linear restoring force, meaning a force that brings our object back towards equilibrium. We always define equilibrium in our system to be a coordinate equal to 0. And the idea of it being linear is that it depends on position. So we've seen that for a spring, it's our simplest situation, and it doesn't actually matter if your spring is horizontal or vertical. In both cases, we have an angular frequency or a period that depends on the mass, and it depends on the spring constant. It is independent, our angular frequency, of what our starting conditions are. So for the same initial conditions, you always have the same period of motion. We then looked at our pendulum, and we saw that we could have simple harmonic motion for either a simple pendulum or a physical pendulum, but we had to use the small angle approximation. So we can only talk about simple harmonic motion of pendula for small amplitude oscillations. We saw that the period, or again the angular frequency, is independent of mass in the case of the simple pendulum. In the case of the physical pendulum, it looks like it depends on mass, but remember that moment of inertia I has mass in it, so actually mass would cancel out of these. And again, it's independent from the angle you actually started at. And we could express its equation of motion in either terms of s, our arc length, or theta, the angle, and over here for the physical pendulum, we typically only refer to that in terms of theta. Conservation of energy is very important, and some of the original calculations we did used conservation of energy to see the relationship between the variables. And as long as we have no dissipation, so no friction or air resistance to worry about, we know that the total system energy is conserved, so K plus U is going to be constant. We know that in the center position at equilibrium, force is 0, potential energy is 0 at that point, so all of your energy is kinetic. At the furthest points, the turning points, you have maximal potential energy, and your kinetic energy is 0 there. So we have two different ways of then writing the total energy based on that, and we can actually use then any other point in between. If we know what the position is, we can calculate the speed, or vice versa, using conservation of energy. Lastly, we then moved away from simple harmonic motion to talk about damping. And damping is what happens when you do have some sort of drag force, such as air resistance or friction. And in this case, the drag model we're using in particular assumes that it is proportional to velocity. So this would not, for instance, be friction. So in this case, we would say that it's negative b, where b is our constant, times v. So that means it points the opposite direction. We get a different differential equation that describes the motion, and that means we get a different solution. And we see that now we have this exponential term out front, which describes this envelope, talking about how the amplitude changes, and we still have this cosine term. If it is lightly damped, then our angular frequency is the same as it would be if it was an undamped system, but if it's a heavily damped system, this omega is actually quite different. We can talk about the time constant for energy loss using this. There is a factor of 2 here, so you need to account for that one way or another. Lastly, when you have resonance, that is the situation where you are actually pushing your system externally with some sort of periodic push. So again, you have an oscillation in how you are giving an external push to your system, and resonance occurs when the natural frequency of your system, which is what we've been calculating up till now, actually matches how you're oscillating it at. And you might be familiar with this from, say, being on a swing, or the idea of breaking a wine glass with your voice, or a sound. There are 2 new models. The main model is simply simple harmonic motion. So we have equilibrium position that we oscillate around in a sinusoidal fashion. Now, in some cases, this is exact. For instance, our mass on a spring, we have assumed that the spring is ideal and that it's isolated. There's no friction, no air resistance. Now, in this case, this would be exact. In the case of a pendulum, we've had to use the small angle approximation, so the simple harmonic motion then is only an approximation. We always see an equation of motion where we have the second derivative of a coordinate with respect to time. This is just acceleration, but that's going to be equal to negative some constant, which is coming from the physics of the system, times position itself. This is the restoring force. Whenever you have a differential equation of this form, the solution has the sinusoidal form. And we know that the angular frequency is then given by the square root of this. So that's how you can recognize that your system can be modeled as simple harmonic motion, though you've possibly made some approximations to get it into this form. Lastly, what we introduced was the small angle approximation, which you use to simplify an equation that has sine in it, and you can say that sine of the angle is effectively just equal to the angle itself. Now, this must be in radians for it to work, and a rule of thumb is that if it's less than about 10 degrees, again, obviously not in radians, but a number you can probably remember, this is valid. Pushing it to 15 is okay, but if you're dealing with angles of 30, 45, or 60 degrees, you cannot use the small angle approximation. It is necessary for simple harmonic motion in pendula. That's the only way we can even solve it. And all this is the first term from Taylor's expansion. So obviously you can use Taylor's expansion for other functions as well, but sine is the simple one that works out the best.